want to you want to set up the alignment mask first.
Yeah. Thanks, man.
Okay, there you're good.
And just verify with the summit that it's okay to execute. It's always best to double check.
It's okay to execute right now, right? Summit.
Hey guys, can you hear us?
John, are we going to hear the math?
Yes.
Thank you.
Thank you.
Did we already aligned mass for
Yeah, so I think we're in this step, right?
did we also align mass 5?
No, you only do one at a time, right?
Yeah, like which one are we on right now?
4.
4.
So we are
Okay.
following the path.
Okay.
That was
Oh, okay. We were just
we added
checking if
this.
3W was here uploaded or not.
right. That was in this list.
Okay.
Yeah.
Okay.
So Ekta, we can just do a quick course align on the imaging. Usually you don't have to do this for Mospire, but maybe let's just give it a shot. So that would be in tel status.
Here, right?
Yep.
Yeah.
And then you click on the tab imaging course align. And I'll share that screen so everybody can see. Or sorry, what am I talking about? Guider course align.
So yeah, usually with guided coastal line, I think you have to select your mask. You just need to grab the guided image.
Okay.
Yeah, you can start course aligning whenever you're ready.
So then you click on the one of the stars there, one of the brighter stars.
Okay.
On the guider image. There you go. And you move telescope. And that looks pretty good. So then we can move to the final line process.
Of course. I guess we did course. Right.
And you can click on start final line. Perfect.
Just real quick, someone in the chat asked us to summarize what's going on. But yeah, we'll talk about it once we're all set up here. It's a pretty busy time.
Yes, turns out the most. No. Was that you, Tenshu?
Oh yeah, no, I just try to remind. I mean, since we are doing alignment, you can put in your object name in the exposure control.
Yeah, so active in the Mospire desktop on Control 0, you can start putting in the information about this mask. Yeah.
I took it here in the.
Yep.
Exposure complete.
Could you remind me again, what are we supposed to put here?
So
Yes, for the object, you can put the mask name. And then for integration time for K-band, we usually do 180 seconds.
Oh, here, duh.
Yes.
I was looking at like this other thing was blinking. I was like, okay,
I thought you found out because you clicked on it.
that's probably what I did. Okay, yeah, object. Why?
So actually, you would just put so the mask name in the object field. So just PCL, so on and so forth.
I was using my laptop.
Exposure complete.
Object.
All right, and then actually we want to go back to the fine alignment screen now. And just make sure that's going okay. So it looks like they all look like they're actually stars. We'll send moves and retake.
Yeah. Okay. Cool.
Perfect. We got stars. That's a good sign. That's not a guarantee.
They're in the last couple weeks.
Hey, Ben. Where do I get the mode for log sheet?
So the log sheets, you open up a web browser and you go to the
No, sorry. I mean, there is a column for mode. Do I read it off of screen for FAXM?
I think that would be just spectroscopy, wouldn't it?
So guys, I'm just gonna hold up on that question, Preeti, just because let's wait. We don't need to do that right this second. So let's just make sure we concentrate on the most important thing, which is getting aligned right now. So even Ekta, don't worry about the object name. Let's just go ahead and continue the fine line process, because we're gonna have a little bit of time to, where we set up the science mask. So it looks like we're doing a lot better now. All the stars look to be in the boxes. And did you send moves and retake?
Yeah.
Okay, perfect. Yeah, so it looks like we had a 0.44 arc second offset in X and then 0.14 offset in Y. So we're getting pretty close. So this hopefully will be dead on, and then we can quick dark, and then you can set up the science mask and then execute the mask.
Sounds like that. Excuse me, everybody.
Exposure complete.
Okay, we're dead on, right on. So you can quick dark.
and then that's where we want to mark base as well.
Thank you very much,
Huh?
Ben.
You want to let the OA know.
You're
you
all
wanna mark base.
aligned? Are you guys aligned?
right there outline.
Okay. Cool.
Yes, yeah,
Mark
please
base,
mark
yeah.
base there.
Okay, and then you would set up the science mask, Ekta, on control 1. That's okay. And then we're in a good rotator angle, but it's always a good habit just to make sure from the summit that we're okay to execute, even though we don't have a choice at this point. So it's
Yeah,
just,
you're very correct, too.
yeah, good, thanks. And that's good. And so now we need to set up everything in the exposure control. So that means like the most important thing, the object name, I mean, you got it, but it's not really that important, but we need to change the integration time. So in the plan for the night, we have the everything you need for that, but I can just read it off. So integration time is 180. Then we have one coaddition. We want to make sure that so that's all correct.
Is this
So MTDS, that's correct.
Okay.
And 16 reads is correct. So the nod amplitude right now is 1.5 arc seconds. We want it to be 1.25 arc seconds.
not amplitude? Well,
So that would be under
Yeah.
edit params.
how do you?
Go to edit params.
Okay.
There you go.
You said, what do we want this?
1.25.
Hey, Shinzo. I saw I had a missed call from Elena at like 11 o'clock. Was there some issue that you guys figured out?
Oh, yeah, it was, so her internet was dropped. So then she called me, so I can,
And then we want a dither pattern of mass nod.
and then her internet was back again in like 10-20 minutes.
Okay.
So,
Okay.
yeah.
And you can go to dark spectroscopy K. Down at the bottom of
Dark.
that. No.
Dark.
Okay. I hope this. Yes. I guess.
Ooh,
Yeah.
Saved by the Bell. So we have the, okay. Okay, so yeah, never try to stay away. It's probably my fault because I told you to go to the top at the beginning. But yeah, stay away from the top. So just think of the top part of that as being real, like going on the sky, and then the bottom part of that is all the dark stuff. So just stay with dark.
Okay.
when
But
anything's
for
moving.
right now though, go to K. Go to regular K.
Yep.
Because the mask is ready to start being observed. If that makes sense. So click on K. Yep, there you go.
Okay.
Good. We're moving. We're in location.
And so you can hit the wait and go, the green wait and go button. And then once the filter is done moving and the grading is done moving, it will start exposing.
And so we're going to be on this for an hour. So you just did what did you do? How many ones? Repeats 1. Oh, okay. So yeah, this is just 1 repeat. So you'll just have to update this as we go, Ekta. And you can do multiple repeats so that we don't have to keep updating it. But yeah, we're going to be on here for an hour.
Yeah.
And you can hit wait and go again. Sometimes if it takes too long after you hit it the first time, it'll time out. So hit wait and go again. There you go. Okay. And now we're taking data.
Yay!
Yay.
Good job, team.
Good job.
Ooh, that was a lot of excitement.
Definitely team effort.
I always forget. I learn every time and then I
Yeah.
always forget.
It's like small little things.
Okay, so we can actually start the Shadow the Scientist session. I guess we have already, and we've taken some observations and got a line, but we haven't actually contextualized anything that we're doing here or nor introduced ourselves. And Roy, thanks a lot for chatting with everybody beforehand.
File number
What?
in the logs.
Uh-huh.
Did you write the file number? A file name?
So Priti, I'll just mention before we start, the logs are all done electronically for Mossfire. So we actually don't need to keep logs like by hand. Is that what you're talking about?
Yeah.
Yeah, I just I usually write down like at least like just the starting or something. Do you have a rough idea? But okay.
So Ben's doing that too.
Venice?
Yeah, because
Okay.
I wanted, but I
Yeah.
wanted to do it, but I guess last time I did it was for demos, not for the.
Yeah, keeping up with Mossfire. I know Ben is very good at it. Keeping up with Mossfire. I usually do handwritten logs, but it's just too frenetic for me. So I'll keep track of like the seeing and stuff like that. But I'll keep. So there's the electronic logs on the ops logs for. You can have a running log in the terminal window, or they have a web-based version. And then just kind of keeping track with the tracking script is fine.
Okay.
So yeah,
Sorry, I just want to update real
Yeah.
quick, and I guess also for the summit. So we use the slit alignment tool to double check the scene. We get 0.8 or 0.9 arc seconds. So I don't know if that helps with mirror calibration or not.
thanks, Ben. Yeah, that's it. So they were getting the Myra in I guess, and in I band, and
J.
this is what H or K that we were looking through. No, we were looking through J.
Yeah, it's the slow alignment tool is J.
So
That was K.
for Myra, they are pointing at different locations. So your target is at very low elevation right now.
Yep.
Yep.
Yeah, so it's right. It's a rising target.
We're looking at K, not
Yep.
J.
Yeah, seems reasonable.
Totally. Okay, so yeah, let's get started. So I'm Brian Lemaux. Aloha, everybody. I'm an astronomer at Gemini, at the Gemini North Telescope in Hilo, Hawaii. So I'm observing actually from our base facility on Keck. So Gemini is a 8.1 meter telescope, which is couple thousand feet away from Keck on the summit of Maunakea, towards Hilo, where I live on the east side of the island.
Exposure complete.
And so there are a bunch of people on the call tonight that are doing the observing. I'm helping with the observing. And so maybe I'll pass to Ben to introduce yourself and what your role is tonight.
Yeah, hi everyone. So my name is Ben Forrest. I'm a postdoctoral researcher at the University of California, Davis. And so I'm currently in Davis, actually, at my house right now, observing remotely. And so, yeah, so I've had a lot of experience with the Moss Fire, and so I'm kind of helping support this observing run. And I've kind of started to put together a lot of the data that we're going to be looking at tonight. But yeah, the people who will be kind of in charge of running the telescope are Ekta and Priti. So I'll pass it over to Ekta, and once introductions are done, I'll talk a little bit more about the instrument. But...
Hello, everyone. I'm Ekta Shah. I am also a postdoc in this group at UC Davis, and we all study protoclusters that we will talk about later on. So currently we are taking observations for some of the galaxies and one of the cool protoclusters. And yeah, so I'm running the telescope, but of course with everybody's help. So let's hope we get some real good observations. And I'm looking forward to interacting with you all as well. So thank you for joining us. Priti, do you
Okay,
want
I guess I'll go. Hi, my name is Priti Staab. I'm a fourth year PhD student at UC Davis. I'm Brian's student, but I also work with Roy and Ekta and Ben. I work on protoclusters. Like our whole group works on protoclusters. I work on one of them right now, and I study how fast the galaxies in this structure form stars. So that's what I'm doing right now. And tonight I am going to well, first learn and then try to drive the telescope later.
Yay!
Yeah, it's awesome that you guys joined, and it's great to have you here.
Priti, would that be your first time driving? I think not, right? You've driven for another instrument, right? For the optical spectrograph, multi-optic spectrograph, or one of them on Keck. It was Lemaux.
No, actually, I think I did. I think I drove Mossfire like 2 years ago.
Okay,
So
it all kind of blurs together.
I forgot everything. So
Yeah. So yeah, just for context for everybody. So so we apply for time on the telescope. So this is a process where we submit a proposal to observe on a telescope. Like Gemini has a proposal process, Keck has a proposal process, and different institutions, different partner countries, different places in the world can apply for time. Oh, actually, so yeah, just update that repeats to like 3, let's say.
Okay.
The repeats box. And then you can click wait to go. Yeah, perfect. And so yeah, so we apply for Keck time, which is the telescope that we're using tonight, one of them, Keck I, through the University of California, Davis, which is my former institution. And it's where the home institution of Priti, Ben, and Ekta right now. And we also apply for time through University of Hawaii Institute for Astronomy, which is Roy Gall's home institution, who was talking earlier in the call. And so we're taking observations now that are part of a 6-year process. So this is part of a process that's been ongoing since since I moved to Davis from France for my first postdoc in 2016. So when Priti says, yeah, I might have done it 2 years ago, these nights on the telescope are very, very precious. We have to convince people that what we're looking at is a good idea. And there's a whole process associated with that. It's a peer-reviewed process. So people from all over the world determine whether or not our idea is good and allow us a certain amount of time on the telescope. And so, for example, for tonight, we have 1/2 of the night. So we've just started. And we're going to take observations all the way until sunrise, maybe 40-30 minutes before sunrise. And we're completely beholden to the weather. So if something's going on in the Mauna, if it's cloudy, if it's humid, then we are in trouble. And so we have to wait, and we have to reapply for telescope time. Very luckily, even though it's been really bad weather for the last week and a half, we have amazing conditions tonight. So I think you heard the summit and Ben mentioning something called seeing, and we can talk a little bit more about that later. I think actually Priti might talk a little bit about that in her talk. So introduction to kind of what we're doing tonight. But seeing is kind of the resolution of what you're seeing on the sky. And so there was a unit that we'll be referring to a lot called arc seconds. And arc seconds is 1/3600th of a degree. So a full moon on the sky is roughly about a degree or half a degree. A degree on the sky is also if you hold your finger at arm's length and you cover up a portion of the sky, that's a degree. So if you divide that into 60, that's 1 arc minute. And if you divide that into 60, that's 1 arc second. So it's 1/3600th of a fingernail at arm's length. That's kind of what we are seeing stars, the size of stars with this telescope tonight. And we have no clouds, no humidity. So we are very, very happy. So, Roy, I don't know, did you officially introduce yourself or tell people where you're from? And I think you're on mute, right?
Sorry, since I'm on my phone, there's all these screens, it was hard to unmute. So I'm Roy, this is my bedroom. But I'm at the University of Hawaii Institute for Astronomy, as Brian mentioned. So I'm a collaborator on this project, and also with Raja Gatakurta, Brian and I help run these Shadow the Scientist sessions, and I do public outreach. So I'll be sort of trying to bring things down to a more general consumer level for people to understand what we're doing, much as Brian was doing with explaining arc seconds there. So I wanted to point out that one of the things that you'll be seeing is that Brian, for instance, is a very experienced observer. He's actually at Gemini Observatory as a staff scientist who does science, but also helps run the telescope. And other people on the team are, increasingly junior, so have less observing experience. So in addition to just doing science, we're also, and talking to you in the public, we're also training up the next generation of astronomers. So for instance, Priti is in graduate school now working on her PhD and has some observing experience, but we're training her up to be able to run the telescope on her own. So you'll be hearing conversations, and that's why you heard earlier, if you were here at the beginning, Brian and Ben explained to Ekta what to do and then explained to Priti. So there's going to be a lot of communication like that as well. And the other people who are on the call that you might be hearing are the actual staff of the Keck Observatory, whose job it is to drive the telescope and also protect it from us doing something that we're not supposed to do with it. And we're mostly controlling the camera that's attached to the telescope and taking the data. So I don't know if the staff will introduce themselves or not. as part of the process.
Hey, you guys, can you hear us?
Yep.
No, sorry, I was talking to the summit.
Summit.
Would you like to introduce yourselves to our Shadow the Scientist people?
Yeah, 1 second, we're looking at their thing. There's
Okay.
some things in the door right here. Yeah, so hi, I'm John. I'm a telescope operator at Keck, and this is Max. He is actually our newest telescope operator. So I've been working here for about 6 years, and Max has been, this is his first shift up. So yeah, so we run the telescope and the dome and the facility, and we keep an eye on safety of this facility, and yeah, try to get good science. It's a pretty chill night tonight, since you guys are looking at just a couple of targets. Yeah. And so at Keck, we have a full-time staff of operators, and then Shan So, who will probably introduce himself as a staff astronomer. So we're up here every night, year round. We work these weird 5 on, 7 off shifts. So we've been up here for 5 days now. Yeah, I got one more night.
Oh, gosh.
Oh.
Yeah, we stay up all night.
Yeah, just for context, they're at what, you guys are at 13,400 feet, something like that.
Yeah. So we're at the summit. Yeah, so it's yeah, I think that's about right. Yeah. So we sometimes run from the summit. We sometimes run remotely, but right now we're at the summit, so we can walk the telescopes back over here. Just on this side of this window that's boarded up, because they put a window in here that decided that was bad. So,
Nice.
yeah,
Nice.
it's nice. Yeah, we get them outside to see the weather and everything. It's pretty cold up here for you tonight.
Yeah, you guys are about 3 degrees C up there. So Hawaii's not all beaches and poke, I guess.
Yeah, we had snow 2 nights ago. So, yeah, it's really nice. I mean, you can be up here and you can drive for a little over an hour and then be at the beach. So you can go from snow to beach. People get really excited. They'll come up here and fill their trucks up with snow, take it back home to their families on the coast. It's a really unique, it's a really special place. It's nice to be up here. Work up here. So sorry, we got a little distracted because it's me a bit of fog forming in the north cam. It's hard to tell how far out it is. It looks like it's, I don't know what it's gonna do, but we're okay for now, but we're just keeping an eye on it.
Okay, thanks for the update.
You guys.
You guys are looking at the Gemini cams at the north cam?
Yeah, we're looking at the north cam, right?
Yeah.
So it looks like maybe it'll, I don't know. It's weird. It's kind of out of nowhere. So the humidity is not kicking up or anything.
Yeah, great.
We're not too concerned yet, but could be a quick closure.
Okay, thanks for the heads up.
And they mentioned later looking at webcams. There's dozens of webcams up on the summit attached to the various telescopes. If you just Google like the Maunakea Weather Center, there's actually a group of people here at the University of Hawaii who forecast weather just for the summit of Maunakea. And the webcams from all telescopes are available. And they have very high sensitivity webcams. So he's just put up some view of the webcams there. And even though it looks like daytime, those are actually nighttime current images or loops of what the people are seeing. These are just very sensitive, so they can see what our eyes cannot.
So I'm trying to. Sorry. Go ahead, Roy. Okay, so.
Yeah, so in the cameras here, these are all Gemini telescope cameras. So they're all mounted around Gemini North on the eastern summit of Maunakea. And so we're looking back. So in the north camera, we're looking at these two telescopes down here. It's looking towards Waimea. And this is Keck II on the left-hand side of that picture. So that's the sister telescope to the telescope that we're observing on right now, Keck I. And you can see, so this is going timestamps. It was probably over the last 5 minutes. So at the summit, they were a little bit worried about what's happening in the north. It looks like maybe some fog is developing on the north ridge here. So we're keeping an eye on it, hoping that things stay calm up there. It seems to be not so humid at the moment. But if things start to spike up in terms of humidity, this could be extremely damaging for the mirror of the telescope, as dirt can condense on top of the telescope, on top of the telescope mirror, and can affect the instrumentation. So they will close the dome if they think the telescope's in danger. So really, beyond many other things, and being totally awesome, and doing their work at 13,300 feet, where there's 40% less oxygen than there is in Hilo. They are guarding against overzealous observing teams like us. So we really want to be open. We really want to be taking our observations. But people on the summit are trying to make sure that these telescopes can be used for generations to come. So they take very seriously any possible damage to the telescope. So if we see humidity spike, you'll see the shutter of the telescope, of the dome at Keck II, and next to it is the NASA Infrared Telescope Facility, the one that's moving pretty quickly in the north cam. You'll see those shutters close to protect the telescopes, the mirrors, and the instrumentation inside. So we're hoping that doesn't happen.
I think that's what it is. Just like how we are doing that.
A quick question about the pictures. The telescopes are above the cloud layer, yeah?
Yeah.
So we saw the cloud moving in the far right picture, the top right picture.
Yep. So yeah, so there's a inversion layer here, which usually is about 9,000, 10,000 feet. So there's a visitors information center. If anybody's been to Maunakea, it's right near a place called Halipahaku, which is probably where the summit crew is spending the nights. So this is about 9,000 or 10,000 feet. And so Halipahaku is a place where you acclimate if you're going up to observe. If you need to spend the night after observing, or I guess the day, so there's a lot of really cool information about Maunakea up there and about the telescopes. So when we go up to do day work on our telescope, we'll stay there for about 30-45 minutes. And Halipahaku is actually cloudy a decent fraction of the time. But then when you go that extra 3,000 feet or so, you get above this inversion layer, and you get incredibly clear skies.
Exposure complete.
Very nice conditions. The wind flow is very laminar, so you don't get very much turbulence on the ground or a little bit above the ground. And so that's what makes Maunakea one of the best observing sites in the world, is the ability for wind to go over the telescopes in a very laminar fashion, that there's not a lot of water vapor above Maunakea, in part because of this inversion layer, and that it generally is not cloudy. So you get something like, I don't know, probably 280 nights a year that's essentially no clouds. So there was a question from a middle school student from Yuli about the middle screen. I think so. We were sharing this screen that I'm sharing now, which has a display called SAO image auto display. And I think they asked a question about what does the middle screen show? Ben, do you mind giving the answer on that question?
Yeah, sure. So yeah, I guess first we should talk about, so there's the telescope that we're using, but each telescope actually has several different instruments on it. And you choose the instrument you want to use based on the science you're trying to accomplish or the questions you're trying to answer. And so the instrument we're using is called MOSFIRE. So that stands for Multi-Object Spectroscopic Infrared, Near-Infrared Explorer. I'm probably messing up the order of the letters there. But yeah, so can break that down to different parts. So multi-object means obviously it's looking at multiple objects at the same time. And it's a spectroscopic instrument, which is different from an imager. So with a lot of astronomy, you're used to seeing all these beautiful images from, for instance, the James Webb Space Telescope. And when you're taking an image, you're pointing it at a section of the sky, and you are just collecting all of the light within a certain, what we call wavelength range, which is just kind of a certain region of colors, right? So you could be looking at red colors or blue colors. And so that's what you do if you are looking at an image. Now, if you're taking spectra of objects, what you're actually doing is instead of just taking all of those photons of certain colors and adding them together, and that's how bright an object appears in an image, instead, you're separating out all those photons into very finely spaced bins of color. So you can see how much very red light there is compared to how much a little bit less red light there is. All right. And so what this allows you to do is identify different features or different elements that are part of these individual objects. And then the last part of the instrument, infrared. So this is light in infrared wavelengths, which is light that we cannot actually see with our eyes. And so this instrument is allowing us to see things that we would otherwise be unable to. So yeah, so that's a little bit about the instrument. So how the instrument works is it has this thing you might hear us mention a few times called the CSU, configurable slit unit. And so what that actually is it's this series of 46 pairs of moving arms. Okay, and so what you can say is, okay, there's an object on the sky that we want to take data of, and you take two arms and you move them really, really, really close together so that the object is right in between the arms. And what this does is it allows you to collect light from the object that's in between the two arms, but it blocks out light from nearby objects, essentially. And so that allows you to get a very detailed description of what's going on with that object while not getting contamination from other nearby objects. And so for MOSFIRE, again, you have 46 sets of these bars, so you can look at, in theory, up to 46 objects at a time. In practice, it's usually a little bit less because you need objects to be kind of perfectly spaced in order to use all of that functionality. And so each, yeah, Brian, thank you, has pulled up the MOSFIRE desktop screen there. And so on the bottom left, where you're seeing kind of all those blue lines, each one of those horizontal lines represents one of these sets of bars. And you'll see on each one of those lines, there's a little green vertical line, and that indicates where the gap in those bars is currently located. All right, so if we've designed our experiments right, which we think we have, in each one of those green bars, there is a galaxy.
Yes,
spike in humidity.
Ben, 1 second.
Well, the dome's closing. Yeah. We got humidity. We got a big old bank of fog over us, so we're closing up.
Okay.
Okay, thanks.
See if I want to stop it after this.
Okay. So do I click on like abort frame or anything, or are you guys gonna take care of everything now?
You can say abort after frame, Ekta.
Okay.
So we have we have I don't know, 30 seconds on this.
Okay.
Right.
Well, that-
Yeah, so just to recap, if you didn't hear that, so that humidity, that fog that they were noticing earlier is moving in sufficiently close to be a cause for concern. And so we're going to be closing the telescope dome to protect the telescope and the instruments.
Exposure complete.
And just making a note of that.
Put in a dark filter. So since we're
Oh gosh.
all,
Oh, we got slammed.
Consider like taking down plates while we are, sitting
Mhm.
here.
Cool.
Whoa.
Dude.
What? Okay,
I think we are still connected.
I was just trying to turn up the volume. Okay, I think we're back.
Go back.
Okay, yeah, so unfortunately, that fog that we were seeing in the north camera here, basically just enveloped the telescopes. So hopefully that'll kick back down a little bit, but I think we're at humidity level of something like,
I think it's like 95% right now. If you show the tel status screen, there's the meteorological data on there too.
Sorry,
yeah.
I stole Brian's screen sharing to show this is the Maunakea Weather Center's page that shows what the current observatories have, and you can see here this relative humidity column. There are ones that are in the red. I don't know why Keck doesn't read so high, and then the dew point. The dew point measures basically when water is going to start condensing out. So that means that you're going to start to get liquid with carrying dust and everything else onto your mirror. So once those things turn red, then it's time to close in, even if you're in the middle of taking an exposure. So you might have heard earlier that they were setting up and they were saying 180 seconds. So rather than just taking a quick exposure like you do with your iPhone camera or something, our exposure times for here, we're going to take 3 minutes at a time. Sometimes we take, and then we add them up to even longer than that. If we were in the middle of the 3-minute exposure and dome closing, too bad, then that exposure is probably junk.
Yeah, and I'll share. So Roy, I think actually the Maunakea Weather Center, it sources its information from like the XMET, so the meteorological information from Keck, but it is a little bit slow to upload. So I'll just show a graph really quick, which demonstrates how crazy that was. I have not seen something like that before, actually.
Brian, 1 second.
Yep.
So should we go ahead and prepare for dome floods right now, or should we wait for?
Oh gosh, no, that would be a way pessimistic view of what's going to happen tonight. So no, we're in a holding pattern.
He suggested it.
What's that?
Shinsu suggested it, right?
I mean, we could do.
The dome is closed right now, so it might be a good use of time to take some dome flips.
Yeah, we could do that. It wouldn't hurt. We just have to abort if things look like they are starting to improve. So Chenshu, do you have any idea of how long that process might take?
I think you need to wait at least 10 minutes. So I mean, right now the humidity is high, right? So you need to wait at least 20 minutes when it's dropped below the I think 80%. So it will take at least 30 minutes until we can open.
Yeah.
It might take 30 minutes.
Yeah, and it's a thick fog of cloud right now, so I don't want to be too pessimistic, but it's
Let's see.
right now. See a rainbow. That's nice.
If it came that quickly, it can leave that quickly, hopefully.
It's true. Very true. So, sorry, do you want to set up for dome flats or what?
Yeah, we can do that. We may as well. We can
It's
use
only
that time.
where this target is, so it's not a big slope. Yeah.
I mean, the thing is, we have observations actually of all of these masks except for the last one. So maybe we can take the last one first, and then if we have time, then we can just pop through mass 4, mass 1, and mass 5. If that's good for you, Ekta.
Yeah. Okay, so I'm gonna set up the W1 as alignment mask first. Wait, hold on, let me.
Oh no, so Ekta, so there's a GUI interface for doing the calibrations. And so if you right click on the like any of the background windows,
Yeah.
it should be under, I can't remember, but maybe Mousefire Utilities.
It's actually in the
Oh,
Mac.
that's right. I always forget that.
Yeah.
What is it?
Where is it?
It's in Magma.
Yeah, so if you go, it's either file or tools. If you go under there, there's a calibration, I guess probably tools, calibration tool. And then my control one just crashed, so I will have to restart it.
Yeah, so it's under tools,
Tools.
calibration tool.
Ah, I see.
basically.
Okay.
Yeah.
Calibration tool.
Thank you.
Okay, so let's see what you have configuration for.
So yeah,
Are all flats. and all.
uh,
Okay. So I'm gonna uncheck all this.
yeah,
Yeah.
perfect.
Pretty much uncheck everything.
Yeah. Do we want to keep the long set one, Brian, or no?
No, it's okay.
Okay.
For now, it's okay.
It's just in K, right?
And then just in K. And then I think depending on how optimistic we are, I would say just do the last one. Yep.
Yeah.
And
Are you,
Shanshu, it looks like we're in dome flap position. Am I reading that right on the Faxum?
Are we still splitting?
Oh, are you? Okay.
Yeah. You can see under telescope, so
are we unchecking them because we're doing dome flats?
just about there though.
We're unchecking them because basically you're selecting which mask and which bands you wanna take. So we are just.
Okay, we're in position and I got the rotator parked at -90, so you can set up all the mass moves you want to set.
Great, thank you.
Does this, what's the exposure time? Does this look right?
Yeah, the nominal should be fine. It should be okay.
This should be good.
Yeah.
Oh. I'm just gonna hit go.
While the observing team is observing, I'm answering questions in the chat if people want to read along.
What does this highlight thing mean? Does this mean anything? This doesn't
No,
make-
it doesn't. No, you're good.
Oh, no, all right.
Yeah, perfect. Okay, so
Hey, Brian.
yeah.
Earlier, when I was accidentally about to hit the spectroscopy, instead of dark spectroscopy, that seemed like a really bad move. But could you describe really quickly why that would have been a bad move? Because your reaction was
Yeah.
a little bit strong. Yeah.
Yeah, so that's no, the great question, Ekta. So you have the CSUs moving. I'll put it in let me share that screen so that everybody can see. And sorry, we're gonna get to people's questions in the chat, and thank you, Roy, for helping with that. But we're just doing our last things for calibrations that we can take while the dome is closed. So we're no longer observing astronomical objects, but rather we're observing the inside of the dome of the Keck I dome for calibration purposes. We're just moving everything right now into place in the instrument to make sure that we're in the right configuration to be able to take these calibrations. And with any luck, so you'll see in this Mossfire desktop window, you'll see a setup mask kind of in the middle, and it's this really complicated, silly name. And so this is a slit mask. So Ben was describing how MOSFIRE works. It's a multi-slit spectrograph taken in the near infrared. And you can see the text is kind of small, but running just below this silly mask name is a bunch of rows that say moving. And so these are the configurable slit units, or CSUs. And they're actually bars that move back and forth so that we can get light pass through this basically piece of metal to our detectors. So this is it's different in the near infrared, but this is basically the same concept as you have with a camera or with a telephone camera. And so we just we block out every part of the sky, or in this case the dome, that we do not want to see. And so we just have this little slit of light, and you can see these little green bands running kind of almost vertically. These are our slits that we're making to observe the galaxies that we want to observe. But right now we're looking at the inside of the dome, so we're just trying to illuminate a uniform source, so a uniform source of light through these little slits, and we're going to try to understand what the response of the detector is in these locations. So basically, as you look at different wavelengths, for every photon that comes in, particle of light that comes in, how many times do we detect it on our detector as a function of wavelength? So we want to make sure, because when we're observing things in the sky, they have some sort of intrinsic brightness, and that's what we're interested in. So we're interested in how much light are they emitting at a given wavelength, because that can tell us about pretty much everything about a galaxy or a star. But for example, Priti mentioned the amount of stars a galaxy is forming. So certain transitions of certain elements, one of which is hydrogen, the amount of emission in a certain transition of hydrogen can be directly translated through complicated physics into the amount of stars that a galaxy is forming. But if the galaxy is emitting 15 photons, and we're only detecting, for whatever reason, because we have reflections on mirrors, and we have all sorts of noise, the universe is very messy. Our collection of these data are very messy, even with these amazing instruments, amazing telescopes. So if we only collect 4 of them, we want to be able to make a transformation between those two things. So we want to know that there were 15 intrinsically, and we only detected 4. And so when we take these calibration images, we're actually able to translate, okay, we know that there's 20 photons coming from this calibration source, and we only get 5 of those. So therefore we know we're kind of collecting only 1/4 of the photons. And it's a little bit more complicated than that, but that's the basic idea of why we're taking calibrations right now.
Then neon and argon, both lamps for arcs.
What's that?
Sorry?
For arcs here, for calibration.
What was your question, Ekta?
So do we want both neon and argon? Like, which lamps would be there for the K one?
Yeah.
Go ahead.
No, please go ahead, Ben.
I was just is it still running? Is it still running the calibration? Is the script still running?
Yeah, so on the MOSFER desktop, it's still moving the bars, but because this window popped up, so I just wanted to check like which lamps we want to use, or we can use, right?
So I thought those were selected when you started the script, right? Because I think by default those are the K, neon, and argon, I think, are selected.
That's what I thought too, but then I don't know why it doesn't show selected right now.
No, but it's okay. So I guess we'll just take just taking the flats now, and then we're going to take the arcs afterwards. Maybe we accidentally checked it, or something funny happened when we were doing things. It does look like you have it set for taking quantity 3, exposure time 2 seconds for the arcs. So maybe it's going to take empty arc frames. I'm not exactly sure what's going to happen.
Yeah.
If that's what happens,
Yeah,
we'll have to.
Yeah, you can also check the looks and see if there's arc in there. So if that's the case, you can, double check the images, and if it's there, it's probably just the arc window is not showing correctly.
Okay.
Yeah, great. Thanks, Chanshu.
So both of them, right? Both neon and argon?
But I don't think you can.
You don't want to change anything right now when the script is running.
Yeah.
So just leave it for now. And yeah, I'll keep an eye on it and we'll see if it ends up taking arcs. And if not, we'll just add that to the list of things to do at the end of the night.
Sounds good.
So why aren't we just aborting it?
No. So no, you don't want to do any frenetic things with the telescope, because when you get into those phase spaces, it makes it, things can go wrong. And so you just kind of let it pass through. We may or may not have checked things. It may have grayed out things. We're just going to see what happens. As Ben said, either the arc lamps will come up or they won't. And if they don't, then we'll throw them away. We'll throw away those images. And then we'll take new observations.
Complete.
And I think that was a flat, yeah. So so no worries. We're not
Usually relate come first, and then the arc will come last.
Okay.
Yeah, perfect.
It's turning lamp on, so I think so.
Exposure complete.
But yeah, we're under no pressure right now. It's okay. We're sitting at pretty bad conditions, so we don't need to rush through this process at all, Ekta. So no worries, no pressure.
Exposure.
Unfortunately.
Complete.
That looks like, and no, there's 13 of them. Okay.
Exposure complete.
So Ekta, just to come back to your question that I was slowly getting to. So when the CSU is open, and so we're moving things around. Usually one bar will open like this, and then the next bar will, the adjacent bar will make its move in. So basically you're exposing the detector to a large part of the sky
complete.
as the CSU masts CSU bars are moving. And so you opened up so by not having the dark filter in,
complete.
you've opened up a huge part of the detector to anything on the sky, right?
I
Which
see.
could be
So you
super
can have
bright source.
right.
And so when you just have the K filter in, let's suppose you open it up and there's a super bright star right in the CSU, and that light is allowed to penetrate through into the detector, then we may get persistence. So where that detection remains for some portion of the night. And Mossfire is not that bad with persistence. Other detectors are much worse, or other detectors for other instruments are much worse. But yeah, that can really ruin an observation for at least a portion of the time for certain slits. So yeah, it's always good to do maneuvers in dark mode.
Right. Cool. That makes sense. Thank you.
Exposure complete.
Yeah, so now we're taking the flat frames, right? And then we're going to see on top of these flat frames, which are the thing that I described a little bit earlier. So you trying to understand the response of the instrumentation and the location of all your slits on the detector. We're going to also be taking arc frames, which is what Ekta and Ben were just talking about. And so for those, we turn on a neon elemental lamp, an argon elemental lamp, and we create an emission line spectrum, hopefully, if they turn on. And that looks like potentially a empty arc.
Exposure complete.
That's the flat one, right?
Still flat?
Yeah, it says flat and the object name. Right?
Ah, nice. Yep.
Complete.
Right, we're taking with the quartz lamp on and then the quartz lamp off. So we get the thermal, because we're in K, so we're getting the thermal spectrum, and then we're also getting the thermal plus the lamp on. So that's just take lamps off. option that you can do. So after this, we'll take, so
Exposure complete.
arc exposures, and it looks like Roy just brought up something that can explain what that means.
Yeah, so in this instrument, we're making a spectrum. So we're taking the light from an object and spreading it out into a rainbow, just like the top panel here shows. But instead of a visible spectrum rainbow, we're in an infrared spectrum rainbow. But what we want to know for each object that we're looking at is what the precise color, and we measure that with wavelength, which is a property of the light. What is the wavelength of that light? And the way we do that, when we take a picture, all we know is on our detector, in what pixel are we seeing the light? And so we have to translate that pixel, which is just a coordinate in X and Y, to a wavelength. So what we do is, when we're not taking our science frames, we take calibration data, where we turn on a lamp that has a gas in it. In this case, we're looking at neon as one of the gases. And every element, the gas of every element, has a unique fingerprint of lines at known wavelengths that people have measured before. So for instance, here's neon. This is in the visible, but there's this different but similar pattern in infrared. And if we know what numerical wavelength each of these lines corresponds to, we can map, using math, X, a position on the detector, to a wavelength of light. And because the whole telescope and the camera and everything is moving, that mapping changes all the time. And also because of the way this detector instrument works with these little slits that let the light in, depending on where your slit is located, also changes that mapping. So we need to calibrate this every time. So it's basically like we have a warping, bending, moving ruler, and we have to figure out how to do that. And we do that by using these gas lamps with known patterns in them.
Yeah, awesome. Thanks, Roy. And it looks like
it did not take arcs.
Looks like it didn't take arcs, unfortunately.
Yeah.
Okay.
So yeah, you can just turn off the flats. So you can just do K quantity 0. And then you can click on exactly. Yep.
Go.
And I'll share the screen so people can see.
Okay.
Brian, are the dome flats, are the flats internal or actual dome flats?
Yeah, good question. So for Mossfire, they're actual dome flats. So the arcs are actually internal to the instrument. Chenshu can correct me if I'm wrong, but internal to the instrument, and then the dome, so the flats are dome flats.
Yeah, that's very correct.
So I was talking about the wavelength calibration, but as Brian was saying earlier, we are also trying to calibrate how sensitive the detector is to different wavelengths of light at different places on the detector. Like here's my iPhone.
Exposure complete.
Hold on a second. Let me turn off this silly background, and then you can actually see what I'm holding up. Background effects.
Exposure complete.
What did you do differently for the calibration tool?
Hmm?
Did you do anything different for the calibration tool other than checking K?
No, just check K, and then here I said 0, so it doesn't take any flats.
Okay.
So there's my phone, and inside my phone is a tiny camera which has a chip. And you get a nice, beautiful picture in your phone with no defects.
Exposure
But inside your phone is actually calibrating that image every time and correcting for defects. And so that's the same thing that we're doing. And so the dome on the inside is actually silvery looking. It's metal. So they shine a light on part of the dome, and to a telescope that's completely out of focus. So it's basically like having a
Exposure complete.
projection screen that is evenly illuminated as far as the camera is concerned. And then any changes that you see in the image that doesn't look even is because your camera or your detector isn't responding equally to the light everywhere. And if you look up Keck telescope on Google, you can find great pictures of what the inside of the dome looks like, as well as the outside.
Yeah, and so Ekta, we can go ahead. I looked at the weather right now, and unfortunately, the only photons we're going to be getting is from the inside of the dome for at least the next little while. So let's take the calibrations for the remainder of the masks.
Okay.
And now you all are experiencing
We also take it for long slits, right?
Yeah, long slit, no need. You can go to K quantity 13 for the flats.
So I'll say I normally do a little bit different parameters. We can do 13/3. I'll usually do like 5 or 6 by 10 seconds. But it doesn't really matter too much, I think.
And so Ben, do you want to share why you do that?
Yes, I mean, again, for right now, it really doesn't matter because we're not under any time pressure. But each time you read out an image, there is a time associated with that. And so if you can take fewer images, you do end up saving a little bit of time. But if you have an increased exposure time, you can then get a similar total integration depth, essentially.
And that doesn't saturate the detector at 10 seconds?
Not for K-band in my experience, no.
Nice, okay.
But yeah, I mean, again, for right now, it doesn't really matter.
Unfortunately, we're not trying to save time.
Yeah.
And this is
Yeah, that all looks good.
Yeah, okay.
Yeah. So yeah, unfortunately, right now, it looks like we really have hit a pretty severe fog bank, and the relative humidity is around 100% or so. So that is definitely bad news for us.
Calibrations for all the rest of the parts.
We're trying our best to use the time that we have in a way that gets us some information. So we have taken astronomical observations, and that sound that you just heard was everything setting up for these calibrations that Ekta just started. So we have taken astronomical observations. We were lucky enough to get some in the first 40 minutes to an hour of our half of the night. And so these calibrations will actually be useful for us for those astronomical observations. But what are we looking at if we get back open? I'm going to pass that to Priti, because Priti has a bunch of things to tell us about galaxies and telescopes and other cool things that will contextualize what we would love to see if we open back up.
Oh, wait, can you still hear me?
Yeah, we can totally hear you. Yeah.
Okay.
This is technically crazy, right? The juggling all these different things. Yeah, but you're doing awesome over there.
Yeah, Ekta was like, I can't concentrate. I'm like, yeah, you're doing way better than I would if there was so much going on.
It's crazy. If things are going well, absolutely nothing's happening, right? Like that's the beauty of astronomy. And then we just get our photons, and then we're happy. But tonight it's not only been, all these new technical challenges and everything to try to share things with everybody, but there's just been so much going on in the telescope. So yeah, it's crazy for sure. Not a normal astronomy night.
Yeah. Okay. So I made a little presentation. But before we get started, can any of you want to tell me, why do we use telescopes? I guess I cannot see the chat, so.
I'll let you know if someone writes something there.
Okay, okay. Okay, so yeah, I thought we could do the first part a little interactive before I explain like the basics. Roy already has done a really good job of talking about a lot of them, and so did Brian. So this will be like a refresher. So we use the telescopes because we want to study distant objects, right? So oh, it's not moving. Okay. So there are objects that are far away. In our case, those are galaxies, or galaxies in a cluster. So cluster is, you can think of them as like a big group of galaxies. And the ones that we study, that we mentioned before, called protoclusters, those are actually clusters that are in formation. So they are kind of like the ancestors of the clusters that we see today around us. And so if you want to study them, we have to use telescopes, right? Because they're really far away. So in another way, they're really dim. And to study their features, we want telescopes to magnify them. So that's one of the case. Telescopes also let us increase their resolution. And then one of the best things that I think about telescopes is that we can collect light that is outside of our visible range. When we're looking in day-to-day life, there's only a particular wavelength range that we call visible wavelength. That means that's all we can see with our eyes. And if we want to see the other wavelengths like UV or infrared that Roy mentioned before, we can't see them with our bare eyes. So telescopes let us collect that information that photons have in those wavelengths, and it helps our science. So there are two types of telescopes. One is refracting. This was more like the traditional or the first kinds of telescope. Actually, so we don't know exactly who invented the telescope. There is a dispute, but it was somewhere around 1608 or something when two people applied for the patent. And the story is that this telescope was invented by accident. The person who applied for patent, that I'm blanking on his name right now, he just saw two kids playing with lenses from his shop, and he realized that we could magnify objects using those. So in that case, it was only like 3 times magnification. So it wouldn't be very helpful if we were using that telescope to look at the sky today. But then a year later, Galileo had his own design, and that was, I think, 20 times more magnifying than the first telescope. So he pointed it to the sky, and that's when the whole history of looking at the sky through telescope began. So this is more like a traditional case. In this picture, we have a galaxy, the light is coming in. Lenses are the objects that bend light. So that is why you can see these two rays coming in and focusing. Where they focus depends on their properties called focal length, but I won't get too technical. So once that lens focuses the image, you get a really nice image, hopefully, depending on the alignment. And then you have another lens here because you want to magnify that image because, again, you want to study it, right? So this is how some of the traditional telescopes used to work. And then on right-hand side, there are the problems associated with this telescope. So sometimes you get something called chromatic aberration, or I like to call it rainbow effect. So it kind of, blurs the image. You can see that this was probably Jupiter But because the lens is aligning different wavelengths of light at different position, you don't get a very sharp image. And of course, you don't want that, especially when the details are the important part of what science you're doing. So we prefer now we prefer like reflecting telescopes, which are the telescopes that use mirrors to focus the incoming light. So here the orange ray is showing you how the light is coming in. This is your primary mirror. Oops, I did something. Okay, this is the primary mirror. It's a little curved, so it's focusing the light on your secondary mirror. And that focus light gets into, this is what is called eyepiece. So when you're using this telescope, this is where you're looking. And then you get a really nice focused image. Usually it is easier to construct these telescopes. And if I might add, cheaper than if you were using giant lenses. So, okay. So another important part of these telescopes is that their primary feature is to collect light, right? And so we want to collect as much light as possible, especially when we are looking at fainter objects, because that's what lets it look at those objects by collecting that light for a long period of time. And so if you remember, the area of a circle is pi r square, or you can say it is proportional to the diameter square. And so basically, the bigger your lens or mirror is, the more light you can collect. And so that's why, okay, so that's why if you have like a telescope that you're using in your backyard, of course, it's going to be much smaller than, for example, Keck, right? And so this is an example of the telescope that you might find for your personal use. There is a primary mirror. So this is where the light is collecting. This whole thing is called light bucket. So it just means that you're collecting light inside here. It gets focused on this primary mirror, which is in the back. If you remember the animation I just showed you, this light then gets diverted to the secondary mirror. Then it gets sent to this eyepiece where you're looking. For this telescope, viewfinder is the place where you would basically align your telescope. So much easier than, aligning Keck.
Exposure complete.
So
are you sure about that, Priti? Have you done a lot of viewfinding alignment with in your Astro 10 course?
Complete.
a little bit.
Yeah, a little bit. Okay. Yeah, that can be really tough too. I mean, Keck has a lot of really nice software and stuff like that to help you out. Up when it's just your hands and sky and God, then and I guess you're very lovely Astro 10 TA. Then it can be very, very challenging.
Complete.
Yeah, my roof helper team is great, and I was like, do you guys have a technique, since you probably have more experience with these? Because we have one of these telescopes at home, but they're not exactly the same. And they're like, oh, you just like twist them until it works, like, oh, okay.
Yeah, everybody has their own technique. It's amazing. And it's really neat. But yeah, you're totally right that aligning Keck is a very, very different experience than aligning on the viewfinder. And we also don't have an eyepiece on Keck.
That's true. Okay, so back to this. Here's Keck, and I'm mentioning the diameter that Brian mentioned before.
Exposure complete.
Or I guess I should call aperture. So this is 10 meter, the maximum length, which means you can collect a lot more light than you could with this telescope in your backyard. These yellow rays here are actually lasers. So Keck uses something called adaptive optics, which I don't know, I think one of you mentioned before, I think Roy or Brian. So what is happening is Keck adjusts. So basically you have these lasers that focuses on, let's say, one point in sky, but of course there's atmosphere which fluctuates, and the 36 mirrors that are on Keck, they adjust so that the laser pointing is constant on the sky, even though there is fluctuations. And that is why we can get, I'm probably not explaining this 100% accurately, so please jump in. But that is why we can get a lot better resolution using adaptive optics. And so this is one of the example pictures.
Yeah, so I'll just jump in for a sec, because this is really cool. It's actually not what we're doing tonight. So adaptive optics, you can actually do adaptive optics even with those Meade 8-inch telescopes that you showed. So actually one of my first projects before I was a student with Raja Guhathakurta, who's the godfather of this Shadow the Scientist initiative. I did adaptive optics. So you basically mounted adaptive optics onto a Meade, I think it was 8-inch or 10-inch, and we took it out to the field at University of California, Santa Cruz, by the music center there. And we had this really nice view of the Santa Cruz Bay, and the sky was usually pretty clear. And so adaptive optics basically measures the twinkling of the object that you're looking at, whether that's a planet. In this case, this is what, Uranus. Yeah, so a planet or a star, and you usually use a point source like a star, so something that's, from our perspective, infinitesimally small, and you see how the light flickers. You probe this anywhere between 60 times per second and 1,000 times per second. So imagine that, 1,000 times per second, which is what Gemini does, so 1,000 times per second, and you actually use what's called a dichroic to split the light. So you use a dichroic to split optical light from near infrared light. And I think this will be a near infrared image here, right? So this is, oh, Dupatar. Okay, so yeah, so this is somebody at Berkeley that takes a lot of observations of solar system planets. And yeah, it's at 2.2 micron and 1.6 micron. So that's, those are infrared wavelengths. That's what that Greek mu, and then M is 10 to the minus 6 meters. So this is near infrared light. So the optical light is measured with a wavefront, what's called a wavefront sensor, let's say 1,000 times per second. And there's corrections, there's actuators, so little pistons on the different, so Roy mentioned at the very beginning of this session that Keck is made up of 36, so the mirror, the primary mirror of Keck has 36 segments, which is really nice because you can actually take those segments off and replace them. So you can put new coating on them, make them more reflective without shutting down the whole telescope. Gemini is not like that. We have one primary mirror, and so we have to take off the entire mirror at one time. So, but all these big telescopes have actuators on the bottom, so little pistons, and they move these mirror segments, in the case of Keck, 1,000 times per second. And it's the same light. So the same light, basically the same light that's coming in the optical, it's measuring the scintillation of the star from the atmosphere, and then it's making corrections. So in the near infrared, that near infrared light is set to the detector, and the actuators correct the mirror in the exact way that the wavefront is measured to be aberrant, such that you get a coherent wavefront. So basically, you're getting the waves in the way that they should be above the atmosphere. So you're reaching the diffraction limit of the telescope, or near the diffraction limit of the telescope. And so these images, because our telescopes, as you mentioned, are very large and even larger than the Hubble Space Telescope, which is like 2.6 meters, 2.4 meters. So Keck has a primary diameter of 10 meters, Gemini 8.1 meters. And so you can actually get finer images than you could in space. And even James Webb is a 6-meter telescope. So you can get better images than James Webb, but you still have to deal with the atmosphere being bright in the infrared, and you're not being able to see certain wave bands. And so like the laser there that you showed, which was a really awesome picture looking in the center of the Milky Way, with both of the Keck telescopes for interferometry. which is a methodology that combines the light of the two telescopes electronically. The laser actually reflects off, so basically it excites sodium atoms in the atmosphere, and it causes an artificial star. So instead of measuring the light from a star, you actually have to measure light from a star as well in some cases. But you can use this for making higher order corrections. So there's a tip tilt correction, which is what I used on my 10-inch Meade. So it just does a tip tilt like this. So rotation tilting in X and in Y. But you can also make higher order corrections. You can bend the mirrors in different ways. And so the laser here allows you to make these higher order corrections while using a fainter object to make the tip tilt corrections. So that's basically how adaptive optics works. So we're not actually doing that tonight, but we have done that in the past for some of our observations. And it because we're doing spectroscopy, we're actually not trying to get really nice images. And so as long as we make our slit wide enough, we actually don't care to make our images really, really sharp. And that's very expensive. It takes a long time because we have to make sure the laser is working, and there's all sorts of technical challenges associated with that. You think you have, I think it's 3 actuators per mirror segment, so you have 3 × 36 actuators, all having to be moved at 1,000 times per second. You have your wavefront sensor, all this stuff. So that's a very high level of complexity to deal with. And so, of course, if you need it, you use it, but if you don't need it, then it's okay.
I actually didn't know you could do that with a backyard telescope too. I thought this was unique to Keck. That's so cool.
Yeah. So no lasers, because you're not allowed to have lasers to do stuff like that. Although the lasers are not going to disrupt any satellites or anything like that, but they can be bad for planes. But yeah, so the idea actually was to make a tip tilt adaptive optics system that was very cheap, that we could send out to high schools and do like high school lab experiments. So we actually developed a lab for that, and that's now still run at UC Santa Cruz and some high schools in Santa Cruz area for the advanced astrophysics lab at UC Santa Cruz and for some of the high school astrophysics labs. So yeah, it's totally possible.
Wow, that's
and they use the same technology for correcting. So if you go to an adaptive optics summer school at the Center for Adaptive Optics in Santa Cruz, they'll actually do a wavefront sensor measurement of your eye, and they'll determine how bad your eyesight is. And so so you can actually do reflections off the back of your eye, and then that's how they can tell you what your prescription should be and everything. And they have awards for worst eyesight. So the worst wavefront that comes bouncing out from the back of a human eye, they have awards for that. So I know some people that have gotten that award for going to adaptive optics school. So, but it's all the same thing. I'd say, it's basically, if you have messed up wavefront, you have a blurry image, and so you make a correction with a piece of glass in front of your eyes, and so it's the same kind of thing, more or less.
Wow. Okay.
So sorry to interject. I just wanted
that was great. I learned a lot too. Okay, so using the technology that Brian just mentioned, we can sometimes, using adaptive optics, we can see some of the features better of the objects that we're looking at. And again, we're not doing this tonight, but this is an example. For example, you can see the bands in Uranus atmosphere better. You can also see some of the small bodies that are orbiting Saturn. And you can see that Saturn has many rings and not just one giant ring.
Can I interrupt for just 1 second?
Yeah.
So Brian, you said we are not using adaptive optics tonight. Have we ever used adaptive optics for these kind of projects, or is there a specific reason why we don't use it for this kind of observations?
So we haven't used it for this. So we haven't talked about the survey that we're doing, and I guess Priti is going to be talking about it in a little bit. But that survey's name is, the acronym is C3BO, and that's Charting Cluster Construction. And it's one of those wonderful acronyms that has acronyms embedded in the acronym. with VUDS and ORLs. And so VUDS is an acronym standing for the VMOS Ultra Deep Survey, which is again another acronym, which is an instrument on the Very Large Telescope Array in Chile, where we took some observations that were kind of the foundation of this survey. And then the ORL survey, which is observations of redshift evolution in large scale environments, which is a project that I did for my graduate thesis and over the last 15 years or so. And so for ORLs, we were looking at the same kinds of systems that we're hoping to continue to look at tonight at very, very large distances. This was a little bit closer. This was about 8 billion light years away, as opposed to what, 12.5 or 12.8. So, you know, close by, 8 billion light years. And so for those, so when we looked at these structures, there were certain types of galaxies that we're really interested in, called post-starburst galaxies. So galaxies that have just been quenched in terms of their star formation activity. So they just ceased forming stars. And we knew this as a kind of hint from other observations that we took, but we wanted to get a spatially resolved map of the emission of those galaxies to try to understand something about the quenching processes and, you know, why those galaxies stop forming stars. So we used another instrument on Keck called OSIRIS, which I don't know what that stands for, but, you know, something having to do with adaptive optics and lasers and near infrared imaging. And so this is an integral field unit instrument. So basically it takes a spectrum of every part of the sky that is within the field of view of that instrument. So every pixel we have a full spectrum of, and we use the laser to get really resolved maps of hydrogen and nitrogen emission in those galaxies. So that was something we did probably a year before you came to, the last time we did it was about a year before you came to Davis, Ekta.
Okay.
I'll also add that these, when you do adaptive optics, usually you can only see a teeny tiny portion of the sky compared to how big the field of view, for instance, of the camera we're using today is. So in this camera we're using today, we're looking at 40 or 50 galaxies spread over a decent sized chunk of sky. Whereas these adaptive optics systems, you'd be looking at the details of one of these galaxies. So if you want to look, it's like the difference between doing a census, like asking everyone how many people live in your household, versus going up to one house and having a long conversation about how they live their lives.
Yeah, perfect analogy.
Exposure complete.
Yeah, so you get much more nuanced information on a particular object, but at the expense of not being able to see a lot of objects. Yeah.
Makes sense. Thank you.
So Priti, do you want to continue on? I think we have about 25 minutes formally left in the session.
Exposure complete.
So that we can tell people what we're actually supposed to be looking at at some point.
Yeah, so we're looking at the something called, let me move my zoom from the middle, ECDSS field, which is the extended Chandra Deep Field South. And I probably should have put the position on the sky that this field is here. And I'm trying to find it right now. But I guess without explaining what RA-DEC is, it's kind of hard to talk about it.
Exposure complete.
So, okay, so the protocluster that we are looking at is somewhere in this field. And that's why we're targeting it. And it's at redshift 3.5, which is another way of saying that when this structure was forming, our universe was around 1.8 billion years old. And for context, it is almost 14 or 13.7 billion years old today. So this is a long time ago. And that's
complete.
That's because light travels at finite speed. And because we are looking at such large astronomical distances, it takes light a while to get here when it leaves the source, because it has to travel such big distance. And light travels at 3 times 10 to the 8 meters per second. So
exposure complete.
So this light left the universe when it was 1.8 billion years old, and it's been traveling and finally getting to us. And so now we can observe
Exposure complete.
the cluster or protocluster that was in that stage. So I don't have a really beautiful picture. to
Preeti,
share.
actually, maybe before you get to that, so maybe you could tell people what a protocluster is, how we maybe know there's something there. Like, so you know, you have this big old sky, right? Like all of these things in the sky, and you don't know exactly where to point or what to do. So yeah, but we had to do a lot of observations, right? Or other people did a lot of observations.
Complete.
And so maybe you want to just give a little bit of background to that.
Yeah, so there are large surveys that take pictures of the sky. That's called photometry, which means you collect light in different wavelengths. So as I mentioned before, telescopes let us do that. We can see more than in just visible wavelengths. So some of these surveys, for example, the one I use right now is called Cosmos survey. And so it
Exposure complete.
sorry, it looks at the wavelengths from far UV to IR, which is the infrared. And so we collect light in all these wavelengths using different
Exposure
telescopes.
complete.
We put it together so we know that information of galaxies, because basically what we can understand is just by
Exposure
understanding
complete.
the light that galaxies emit or their stars emit. And of course, there are other physical processes that are going on under the surface as well. So by looking at these, or by looking at the images, I would say, we can tell that if there is a region where a lot of galaxies are together or they seem close to each other, we say this is like an overdensity of galaxy because there are a lot of galaxies there. And it kind of depends on the underlying cosmic web structure, if you've heard about it. And so by knowing where to look, like that's how we figure out where to look. And that tells us that we can go after it, take spectroscopic data, where, again, I guess Roy explained what spectroscopic was before. So that's how we can figure out if there are these structures called protoclusters, which are ancestors of galaxy clusters in formation, if they are
Exposure complete.
if they exist there. These structures are really rare. There only have been handful number of detections so far, and
Exposure complete.
it's getting better with bigger surveys. So as Brian mentioned before, we use one of the surveys called WOODS, which is Lemaux's ultra deep survey. And what this survey did is it looked at almost 10,000 galaxies. And it took spectroscopic data of those galaxies. It looked at really faint galaxies as well. And by doing that, we figured out, okay, there were 5 or 6 of these structures that look like these, basically a bunch of galaxies hanging out together. And we can look at those because this is a special, right? This is a special part because this is a rare structure where a lot of galaxies are together. If you look at just the normal space, well, normal. If you look at the rest of the space, for most of the times, the galaxies are kind of scattered away from each other. So we started taking data of these galaxies with Keck, and we use Lemaux and MOSFIRE for different structures. Sometimes we use both for one structure, depending on how far away it is.
Exposure.
Anyway, so we look at these, and one of our goals is to, or one of my goals is to look at their star formation, which is how fast the galaxies inside these structures and outside these structures are forming stars. And it's interesting to look at them because if you look at clusters around us today, for example, Coma cluster or Virgo cluster, right? These clusters of galaxies are not forming a lot of stars, but we see abundance of stars. So they must have formed at some point as the universe was getting older. So we started looking at or I guess not just we, but us as astronomers and scientists started looking at what does the history of the star formation look like? And we realized that even though most of the galaxies in these structures are not forming stars today, as we go more and more back in time, they were forming lots of stars, which is wonderful but perplexing. The problem is, why is that the case? And that is one of the questions we're trying to address by studying these structures. Again, these are really rare structures. Unless they're really massive, you can miss out on them really easily. So yeah, so by study, there aren't a lot of these detections, but what we have based on that, we are trying to study this question of why galaxies that are hanging out together or in a cluster close to each other are special compared to the galaxies that are just scattered away from each other. Okay, that was very, very long speech.
Oh, that's okay. Thanks, Priti. And yeah, like just to give people an idea, the clusters of galaxies that Priti is talking about. So I would say like the Coma cluster is a good example, Priti, of like a nearby cluster, very, very massive system. So this is so it's, you know, like 1,000 Milky Way type galaxies all together. And so like we have in our local neighborhood, which consists of the Milky Way, Andromeda, and some smaller satellites, galaxies, we have 2 galaxies, Andromeda and the Milky Way, that are about as bright as the Milky Way. But in the Coma cluster, yeah, you'll have, in the same kind of volume, you'll have thousands of galaxies. And so this is a very, very dense environment where galaxies interact with each other gravitationally. They strip gas from each other, and they cause the excitation of black holes that are sitting in the centers of galaxies. So active galactic nuclei is what we call them in astronomy. So basically gas funnels to the center where a massive black hole sits, and these galaxies excite, and the black hole excites. And this can cause a great amount of feedback for the galaxy, meaning a lot of very energetic radiation that can destroy gas, disassociate gas, and stop star formation. And so as these galaxies coalesce into these structures and interact, they can go from being very highly star forming to not forming very many stars at all. And so as Priti mentioned, in the local universe, not so much the Virgo cluster, but the Coma cluster, definitely the galaxies have basically stopped forming stars. But as we go really far into the distant universe, the galaxies that are coalescing into the beginnings of these kind of cluster environments, they seem to be forming stars at a much higher rate than galaxies that are sitting isolated by themselves. And so we're trying to determine how that process occurs, how that assembly process occurs, and what happens to those galaxies as they fall into these very young structures. And there was a question actually, Priti, in the chat about where this image is from. And then there was a question about the bright objects that have a pattern of fainter off-center circles around the really bright objects.
So this image is like a 3-color composite image from wide field imager on the let's see, I have it here, 2.2 meter ESO telescope. That's my source. So this telescope is in Chile, and it's called La Silla Observatory. But
La Silla, okay, yeah.
Yeah. Okay. Yeah. So that's where this image is from. I got it off of Wikipedia. And the spikes are probably the stars. I'm not sure about the halos around them.
Yes, the halos are going to come from the internal optics of the telescope. So these should be reflections of the primary mirror. That's kind of there's so much light from these stars, and you're taking an image for so long that it actually you get these internal reflections, which causes this halo around the bright objects. So you don't see this in the fainter objects, but you even like the kind of fainter-ish stars in the image, you can still kind of see the reflection of the primary mirror there. So like the one down at the bottom left, you know, it doesn't look like that bright, but yeah, you can definitely see this offset reflected image of the primary.
Yeah, okay.
Yeah, so the universe is messy. So that's not intrinsic, right? That doesn't exist in the universe. That's a function of our observation, right? And that's really important because we spend a very long time, you know, we're taking these calibration frames right now. We spend a very long time trying to calibrate out all of our ignorance from these observations because our instrumentation is not perfect, but we can make it as perfect as possible by understanding the parameters of those observations and controlling that experiment very, very closely. But even after all of our work, you know, and all of the effort that goes into trying to understand how our raw observation maps over to the intrinsic properties of the objects, we still have residuals left. And so we still have to deal with that. I mean, a lot of grad school, postdoc work, you know, faculty work has to do with trying to understand, okay, what, like, how do we quantify our ignorance? How do we, what's wrong with the images that we take? What do we not know about, you know, these images? What do we not know about the properties of these images? And how can we make models to try to, in some way, mitigate that ignorance? And so, I mean, just a group meeting this past week, we were talking about, you know, we have probability density functions of how distant something is right in the sky. So we don't know, we just take the different colors of light and we fit models to it. And we try to determine how far away is every single little dot in this image, right? But we don't actually know, we just have a probability distribution. And so it's maybe, you know, 10% that it's like right close by and it's just a really dim object, or, you know, 40% that it's kind of middle distance and a little bit brighter, and 50% that it's, you know, really, really far away. And so, but, you know, that probability is only as good as our calibration processes and our measurement processes. And so we spend a lot of time trying to get that correct. And you see still in this image that there are some residuals that are very hard to cut out. So like when we take a catalog of all the objects that are in the sky, in this image, in this part of the sky, we actually don't trust. So we use something called masking to say, hey, we don't think that this part of the image is necessarily reliable to the level that we need it to be. And so we're just going to kind of trust those data less. And we won't use that as much, or we'll, you know, put a kind of a disclaimer around that saying, yeah, maybe that's not something that we want to use unless it's an emergency and we absolutely need to do it. And then we have to take that, you know, very cautiously.
Yeah, that makes sense.
So even a beautiful picture like that is still a lot of danger.
Quick question. So how does the weather look?
Unfortunately, it doesn't look like we're going to open up during this session. But we're still having a lot of fun. I wish we were on Sky. I would love to be on Sky. But we did our first Gemini North Shadow of the Scientist last Friday, and we were closed the whole entire time. We had a blast. So yeah, but unfortunately, it doesn't look like it's clearing up.
Okay.
Okay, this is the last slide. And I just want to say, please ignore most of the stuff that's written here. It's very technical. But what I'm trying to show you is, so this is not what we are exactly seeing on the sky.
Exposure is complete.
It's one of our techniques that lets us, what we say, reconstruct the sky, basically, focusing on the structure that we're interested in.
Exposure complete.
This is what is called a VMC map that one of our group members, Denise, who's actually at IFA, and she's about to graduate. She's
Exposure
has she
complete.
created this one? I just assume that all the VMC maps are created by her.
Oh,
Brian?
no, I make the VMC maps. Denise uses them. She's like super awesome at using them to find structure.
Exposure.
So
Okay.
she takes the maps and does awesome things with them.
Okay, so Brian has created this map. And so the red parts here are where we think that most of the galaxies inside this structure are. So these are the dense parts where, as I said, the galaxies are hanging out together. And then the green parts would be where we would still see some galaxies, but they would be scattered far away from each other compared to these galaxies. So we are, well, we would be trying to get observations of these galaxies to understand their position on the sky better and their redshifts better. But unfortunately, we're close now. So anyway, so after we've taken our data, we would be able to
Exposure
see all
complete.
of our galaxies here eventually.
And so, Preeti, can you jump back to the slide before?
Yeah.
Exposure complete.
So in this pretty picture, every little dot there is a galaxy, basically every teeny tiny dot. And for
Exposure.
every one of those, there's a couple of stars, but almost all of them are galaxies. And so for every one of those little dots, we have an estimate of how far away it is. So we actually take what those maps are, is we take slices in distance in this picture. We take a slice closer and further and further and further and further. And then we make maps that show in what part of this picture are there a lot of galaxies at that distance. It's kind of like doing geology and digging through the layers and seeing where there were a lot of dinosaurs living at a given time. And so we take this picture and we kind of turn it 3D. It looks two-dimensional to us, just looks like a flat picture. But if we know the distances to these objects, we can make it 3D. And then it's like taking slices through a cake and asking, when did we run into a strawberry? So, and those strawberries with all its little seeds are clusters or protoclusters of galaxies. And so if you go back to the next picture, then here's this green and red map is like a slice through the cake. And we found a place where there's a pile of galaxies that are all at the same distance from us and clumped together. So that's one of these clusters or protoclusters that we're interested in studying. So that those big red things, so with the black circles around them, are these overdense. They're like the cities in the universe. That's what I always say, is like if you look from space at a map of India or
I love that.
You see like there's the areas where there's nobody, and then there's the areas where there's lots of people. And we're interested in studying the areas where there are lots of people, and why do the people in cities look and act and talk and behave differently from the people who lived on the farms. So and if you look back in history, people in cities and farms behave differently from each other, but in different ways than they do today. And so we're trying to figure out what makes all that happen.
And at different points of history, those differences were also very different. So that's also what we are studying. How did that change with time?
I call it galaxy sociology.
That's awesome.
Exposure complete.
If you make a map of the universe and you look at its structure, it looks just like a map of the United States at night, right? There's the filaments, like the freeways and interstates that connect the big structures, and cars and people move along those filaments into the cities. And actually, the history of the US and most of the world is that the empty parts get emptier and the cities get ever bigger. And so right now we're looking at cities that are being built up and how the suburbs get absorbed into those, and how do the people in the suburbs behave differently from the people in the cities, and that kind of thing.
That was a great analogy, Roy.
So Roy, I just put in the chat our the press release that we had from AAS maybe a decade ago. Oh man, it's 15 years ago. Oh gosh. Okay. Anyways, but yeah, that where you popularized that analogy, and yeah, it's a great analogy. And I just want to mention that one of the like absolutely seminal papers on protoclusters that I've used a lot in my work, that's actually from simulations, mostly simulations of dark matter. The title of the paper is Ancient Light from Young Cosmic Cities: Physical and Observational Signatures of Galaxy Protoclusters. And I thought that was a really cool title. And this was when nobody really knew anything about protoclusters. This was a decade ago, and people were just starting to open their eyes to what these things might look like. We didn't know how big they would be. We didn't know what kind of galaxies would be there. Absolutely nothing. And I thought that was a really nice, you're kind of getting your first glimpse of what these, doing this archaeology and first glimpse of what these things might look like. And it was a really cool time. And now we're into the era of like, okay, we're starting to understand them. We can map them a little bit. And now we can, really start to take some observations that can get to, see the whole entire,
Exposure complete.
the contours of the city, the buildings, the sociology, everything about it, we can start to map out. But it's still very difficult, but we're starting to get a little bit of a picture at this point. But
Complete.
that took us a decade to get to that point.
And I'm about to go to bed because I got to wake up in 4 hours when my kids get up. But the technological advances that have made this possible are pretty remarkable. So back in when Edwin Hubble was mapping out galaxies, he realized that galaxies around us were different depending on whether they lived close to each other or were far apart. And that's sort of on the sort of time scale of 80 years ago or 100 years ago.
Exposure complete.
And then with bigger telescopes, by the 1980s, we were understanding that when we looked back in time a few billion years, we could see these cities like already existing. And then by the time we were doing the work of like that press release, we were looking back at the time when the universe was about half its present age or a little bit more. And we were able to map the cities from that era, similar to how Hubble and others were able to map the cities of today. And now the work that we're doing is we're trying to map cities back when the universe was only 10% of its current age or 20% of its current age in almost the same level of detail. So we want to see, like, I don't know, I'm from New York, so I'm thinking of, we're trying to see New Amsterdam in the same detail that you could see New York today. And that's only made possible by having bigger telescopes with better cameras and that can take more spectra or bigger pictures. And so it's technology really, it drives a lot of our ability to do this. So I'm going to sign off and say good night, or to many of the observers in California, where it's already the wee hours of the morning, good morning.
Morning. Thanks, Roy.
Thank you, Roy. Thank you for joining us.
Yep.
See you next time. Good
Bye.
night.
Well, good night.
And just to answer the, sorry, I've been quiet, my voice is kind of going, but there's a question in the chat about how much usable data we think we got this evening. And so we did get about half an hour or 40 minutes of time exposing on some of our science targets before the fog rolled in. So we take every bit that we can get. So that's definitely much better than not having opened at all. But of course, it would be.
And I don't know if you guys been watching the weather, but the fog's kind of clearing out. The humidity's tanking.
Yay.
Yeah, so all the sensors just went green. So just as quickly as it, just as quickly as it came in, it's popping out.
Okay.
Yep.
And it looks like
So
we
we're
are.
gonna get on a,
Mhm.
it's gonna be a 20-minute clock until we can reopen again. So check back in at like the flight time.
Cool. Thank you.
To what?
Okay, thank you guys.
You said 250. Oh.
Yeah, so right when we get the good news, then
I guess the thing, no blast, or are you done with those?
No, it looks like we are done with those. Right, Brad? That's
Yep, that script finished.
Okay.
Okay, I'm gonna slid the telescope down horizon.
Okay.
So yeah, right when we got the good news, looks
Wow.
like when we were scheduled to end the Shadow of the Scientist session, and probably since we have a 20-minute clock before we even have a chance at opening up, we'll probably call it for tonight in a little bit. But yeah, we can at least preview that we may get something later tonight, and that would be awesome because yeah, 30-40 minutes is great. It's really wonderful data, I'm sure. But we would really love to get a couple more hours because that will allow us to get enough data to probably determine the distances to a large number of galaxies and be able to understand the properties of those galaxies. So yeah, that's the hope. And if we're not able to open up tonight, then probably our next time observing this target with this instrument will be a year from now. So this is really, really important that we open up, and it's why the people on the summit are guarding us from overzealously opening the telescope, because we were really, really eager to observe. But you can see on the screen I just shared that the humidity, which is the teal line in this Keck I Met graph on the right plot, dropped very precipitously. So it went from 100% all the way down to about 50 or 60%. And so as long as these indicators, this primary dew, secondary dew, outside dew, and precipitation all stay green or yellow for another 20 minutes, then we should be good to open up. And it looks like the humidity is creeping up again, unfortunately. So it's probably going to be one of those nights that we're kind of jumping in between opening and closing, which is how a lot of astronomy goes.
Yeah, and as I think Bran mentioned at some point, or Ben mentioned at some point, like we have been taking these observations very periodically. So sometimes like every year or every few months or something. So for some of this mass, we.
Hey, sorry guys, I just want to interrupt real quick. I'm gonna go into the dome and look for drips. So we're gonna be using flashlights. So just make sure that dark filter is still in. I see it's in now, but just a heads up.
Okay.
We're using flashlights. Thank you.
What we say, Ekta?
What was I saying? Oh yeah, so I was saying that for some of this mass, like we will take multiple observations during this multiple runs. So we will take some observations right now, and then if we get night like next year or in January or something, we will take the observations of those objects again. So sometimes you would like combine this multiple observations and then like reduce them and all. So even if like for a given night, we might not get very, very useful observations, we can still add them and kind of use all of them collectively for our science. So yeah.
So Ekta, let me ask you a question. Is that true of every astronomical source, that we can just kind of sit around, wait for a year, 2 years, 3 years, 6 years to take observations and just assume that nothing changes? I mean, why can we do that in this case? And is there cases where you might not be able to do that?
That's a good point. So obviously, if we take multiple observations and we are basically, and we kind of add them together, then in some ways we are assuming that nothing is changing over time. And so then let's look at what are we observing, right? And whether or not something changes over time. So we are looking at galaxies, and without going into too much detail, because even within galaxies, you can have AGN activity and that can change with time. But we are kind of looking at galaxies, and they are relatively simple objects in terms of time evolution. So most of them wouldn't show almost any change with time. So therefore, we can take observations during different types of year. But then again, we also have to keep in mind which field your galaxies are in, because some of the fields are only visible during certain ones or from certain locations. You have to keep that in mind. And let's say if you are observing some sort of like variable star or something, right? And if you want to study its time evolution, then, if it's supernova or something, and if you want to study time evolution, you have to take observations at that point. So yeah, given that we had observing objects that usually do not show significant time evolution or almost any time evolution, that's why we can take observations even during different years and then still combine them. So yeah.
I have a question.
Yeah.
So I know we calibrate and we have techniques to reduce some of the, I guess, atmosphere, but wouldn't the different weather conditions affect the data when we're combining it?
Yeah, it would. That's
Or
why.
is it all taken care of when we're calibrating the telescope?
So I think Brian can say more about it, but basically,
No, please.
So there are different steps in data reduction and calibration, right? So I think ideally what you want to do is you want to properly calibrate individual images and then add them together. So when I take calibrations, I have calibrations for different nights. So in some ways I'm taking that into account, and then I'm correcting for that. And then once it's everything gets same scale, then I'm adding them.
How good is that procedure? Does it 100% correct the image usually? I'm probably not wording my question right.
So if you have a really bad night,
Yeah.
then that's a good question. So that's why me and Brian, for some of the masks, so basically you have to put that question, if you have really bad data and if you add them with good data, then maybe your overall quality is actually decreasing instead of improving. And so so you have to take that into account. I think it depends on how bad the observations are, because if it's really bad, you don't want to add that. So you can do different tests of once you add, how much improvement is there, or if it's really bad, just keep it out or something.
Okay.
Yeah.
So related to that, Aparajito just asked, so you subtract the sky spectra before co-adding the target spectra. And thank you, Elaine, for joining us. Mahalo and aloha. So yeah, how do you do that? And so how do you what's the process that you do when you you have a cloudy night and you want to, I don't know, add that together with a really, really clear night?
Just 1 second. Are you also hearing this high pitched sound?
No, I'm hearing it. I just don't know where it's coming from. Because it just started.
Yeah. Okay.
I don't think it's any of our setup. I don't know. Maybe it is.
I'm just making sure.
Sorry, Brian. We're hearing
just
high
one
pitch noise here. And
Yeah,
I don't
no
know where it's
So I'll take this while you guys are figuring that out. Or did you figure it out already, or is it still going on?
No, it's still going on. I just want to really quickly.
Yeah, so so we don't so the sky spectrum subtraction happens as part of the reduction process. That actually so the arc lamp images that we were taking before allow us to determine what wavelength values are associated with each detector position. We can also use the skylines, so the sky emission, to determine the wavelength value at every detector location. So usually in a lot of spectroscopy, you'll use the arc lamps first, and then you'll kind of iterate around that with the sky spectrum. And so then once you did that, you determine the wavelength at every single location on the detector. Then you would subtract off the sky spectrum. So that's removing what we call the sky lines or the sky glow lines. And but then we also want to do what's called spectrophotometric flux calibration. And this is sometimes where we'll take so the way to do this process is, for some people, they would take a standard star observations. This means you take on the same night, under the same conditions, hopefully, you take an observation using a similar setup to yours that you use for science to observe your scientific targets, at a star that you know how many photons are being emitted at each wavelength. And so, so then you're able to calibrate out again. So if you know, you get 15 photons from the star, and that star is actually should be emitting for your observational setup 30 or 40 photons, then let's say 30 photons, then you know that you're getting 50%. And you can do this for every single night. And so you can, so if you have a cloudy night and maybe then you're only getting 2 photons, so then okay, now I'm not getting as much, and so I have to make different kind of correction. And then so you would, spectrophotometrically calibrate all of your spectra, and then you would co-add them in what we call flux density space, or with these units that are actually physical, rather than just some amount of photons on your detector on a given night. Another way that we do this, and this is actually our method normally, is we put a star on one of our slits of our slit masks. So one of these little vertical lines that we showed earlier is detecting a bright star, or it's trained on a bright star. And we know, again, the intrinsic brightness of that star. And so as we're taking the observations, same setup, everything's the same, it's being tracked in the sky with our scientific targets, then we can combine those all together, all those observations together. We say, okay, there's the star. We get, again, let's say 5 photons. We know that there's 30 that should be coming in at this wavelength. So therefore, there's a correction factor of 6, and we can apply that same correction factor to every single one of our science objects. And so this has the virtue of being done at the same exact time with the science observations. The detriment to that methodology is that sometimes the intrinsic brightness of the stars that you choose to put on your slit mask are not measured as precisely as the stars that you take separate observations for. That's one reason why you might not want to do it. So I think we should probably call the session for the night. So thank you everybody for joining us and for sticking around for 2 hours, even an hour of which we were closed. But it's been very enjoyable. This is, we would normally be reading papers or, doing other things that astronomers do at night when their telescopes are closed. But it's been really enjoyable to talk with everybody about some of the science that we hope to start again in maybe 5 or 10 minutes. So there's going to be several Shadow the Scientist sessions coming up on the sister telescope that we're on now on Keck II, and Raja Guhathakurta is going to be running some of those sessions, and his colleague at UC Santa Cruz, Jason Prochaska, is going to be running some other ones. So these are 2 coming up next week, I think on Tuesday and Saturday. And then the following week, there'll be 2 nights sometime during the week with times to be determined. So you can always check on the Shadow the Scientist website, which I'll put in the chat. And you can sign up there. There's a registration form for the upcoming night, I think on Tuesday. And yeah, thank you all for joining us and for asking great questions and for keeping us honest on our science and keeping us awake as we're trying to move into some more science later in the night. And I don't know, Ekta, Priti, Ben, if you want to say anything before we leave.
Yeah, just as you said, thank you so much. Great questions. Sometimes it also makes us to think about stuff. So as Brian said, thank you for keeping us on our toes. It also helps during this time because it can get a little bit laggy right now. So yeah, thank you. And I hope you had fun, and hopefully the next session, you will see some observations, but I hope you got some idea about taking observations and stuff, and this was useful. So yeah.
Yeah,
Thanks.
yeah, I'll just echo what they're both saying and also mention, if you're particularly interested in the science we're doing, I think the plan is to have another Shadow of the Scientist session for our team in December at some time. So I guess if you're interested, keep an eye out for that. But yeah, thank you so much for joining, and hope it was entertaining and you learned something.
Yeah, thanks for mentioning that, Ben. Yeah, so yeah, I think it's December 15th and 16th, and we're going to be observing the same part of the sky, hopefully, but with an optical multi-slit spectrograph called Lemaux. So yeah, that should be super exciting. Okay, aloha, mahalo, and see you next time. And for the observing team, we can meet up on the Keck I Zoom after this. Okay.
Sounds good.
Thanks, everybody.
Thanks, everyone. Bye.
Good night. Good morning. Good afternoon.